In this lecture, we will talk about density of states per unit energy per unit volume, in which electrons can be filled in the energy levels present in conduction band and valence band. The density of states per unit energy per unit volume in conduction band is usually represented by G subscript C within bracket E, where C represents conduction band and within bracket E is representing that Gc is variable whose value depends on the energy level E. The formula for density of states per unit energy per unit volume in conduction band is given as 4 pi into 2 multiplied by effective mass of electron raised to the power 3 by 2 divided by cube of Planck's constant into E minus EC. This expression is valid when E is greater than or equal to EC. Similarly, the formula for density of states in valence band is given as 4 pi into 2 into effective mass of hole raised to the power 3 by 2 divided by cube of Planck's constant into EV minus E. This expression is valid when E is smaller than or equal to EV. Here, EC is the minimum of the energies of electrons that are considered to be in conduction band. Similarly, EV is the maximum of the energies of the electrons that can be considered to be present in valence band. The Fermi distribution function can be used to calculate the concentrations of electrons and holes in a semiconductor provided the density of available states in the conduction band and valence band are known. For example, the concentration of electrons in the conduction band is given as where GE into DE is the density of states in the integral energy range E, and N0 represents that electron concentration is considered at the equilibrium condition, meaning the electron concentration does not change. Also, Fe is representing Fermi Dirac probability function. This expression is very important. Even though you know the value of GE as well as the value of Fe, but it may be possible that some hypothetical values can be provided in the question and you have to simply integrate the value and find the final result. You can observe that the number of electrons per unit volume in the integral energy range E is the product of the density of states and the Fermi Dirac probability at the energy level E. Thus, the total electron concentration is the integral over the entire conduction band. The result of the integration is the same which will be obtained if we represent all the distributed electron states in the conduction band by an effective density of states Nc located at the conduction band edge Ec. Therefore, the conduction band electron concentration is simply the effective density of states at Ec times the probability of occupancy at Ec. The difference between the terms density of states and effective density of states must be very clear to you, because even though these two terms look similar, they have very different meanings. They have different dimensions, and also if you want to plot the distribution of density of states per unit energy per unit volume, that is GE with respect to energy, then you will get a continuous function, whereas for NC or effective density of states, you will get a discrete value only, as the definition itself says that the effective density of states has been assumed to be located at only conduction band edge EC. Therefore, all the states are hypothetically assumed to be at EC. You have also studied about Boltzmann approximation, which says that the Fermi direct relativity function can be reduced to expression exponential of minus E minus EF divided by kT. And we consider this expression to be true when E minus EF is several times greater than kT. You should also know that for 5% error in Fermi direct plurality function, we can assume that when E minus EF is greater than or equal to 3 kT, then Boltzmann approximation is valid. Now we calculate the value of Fermi direct plurality function at energy level EC, then we will get exponential of minus within bracket EC minus EF divided by kT. Now if you put this value in this expression, then we will get the electron concentration in conduction band to be equal to Nc multiplied by exponential negative of within bracket EC minus EF divided by kT. This is also a very important formula which you must learn, as this formula is used very commonly while solving numerical problems. So until now you got three formulas, and all the three are very important for numerical problems. One is the exact expression in which the integral of density of states per unit energy per unit volume gives us the electron concentration in conduction band. And after that, we get the exact expression of electron concentration in terms of Fermi direct plurality function at energy level EC and effective density of states NC. And after that, we get the formula when Boltzmann approximation is assumed to be valid, which is generally true.